Welcome back to my YouTube channel. Today we will discuss fundamental theorem of cyclic group. Okay, so fundamental theorem of cyclic group say that every subgroup of a cyclic group is cyclic, and moreover, if order of generator of A equal to n, then the order of any subgroup of generator of A is divisor of n, and also for each positive divisor k of n, generator of A has exactly one subgroup of order k, and this subgroup is generator of n by k. Okay, this is a statement of the fundamental theorem of cyclic group. Okay, now proof. First of all, let G be a cyclic group. Okay, so that is G equal to generator of A. Okay, and also given H is a any subgroup of G. Suppose H is a any subgroup of G, we show that H is a cyclic subgroup. Okay, so first of all, if H is identity, then proof is trivial. Okay, now if H is non-identity, okay, and also here H is a subgroup of G, so that is every element of H is also an element of G. Okay, so that is, and here already given G is a cyclic and G equal to generator of A. Okay, that is, and also generator of A form as every element of generator of A form as A to the power n for some n belongs to Z. Okay, so this implies every elements of H is form as A to the power t for some t belongs to Z. Okay, because every element of H is also an element of G. Okay, so now let M be the least positive integers such that A to the power m belongs to H. Okay, so and also H is a subgroup of G. By the closeness property of subgroup, A to the power m dot A to the power m, that is A to the power 2m, also belongs to H. Similarly, A to the power 3m also belongs to H, and so on. And also for hold negative integers, because inverse element, every element has an inverse. So this implies generator of A to the power m is subset of H. Okay, next we show H is a subset of generator of M. Okay, that is, we show H is subset of generator of A to the power m. Okay, so let any element x belongs to H. Okay, so x equal to A to the power k for some k, because every element of H form as A to the power t. Okay, form as A to the power t, so x equal to A to the power k for some k. Okay, so by the division algorithm, there exist integer q and r such that k equal to qm plus r, where r lies between 0 and strictly less than m. Okay, so this implies a to the power k, this equal to a to the power q m plus r. Okay, so this equal to a to the power m dot to the power q and dot a to the power r. So this implies a to the power r equal to a to the power k dot a to the power m to the power minus q. Okay, and also a to the power k belongs to h, and a to the power m to the power minus q also belongs to h. So we have, this implies a to the power r belongs to h. Okay, where r lies between 0 and strictly less than m. So which is a contradiction? Why? Because why? Since a to the power m belongs to h, where m is the least positive integer, but here r strictly less than m and also positive, which is a contradiction. Okay, so this implies r must be equal to 0. Okay, so we have, suppose this is equation number 1, so we have from equation 1 a to the power k equal to a to the power m to the power q. Okay, and also a to the power m to the power q belongs to generator of a to the power m. Okay, so this implies a to the power k belongs to generator of a to the power m. Okay, so this implies x belongs to a to the power generator of m. Okay, so therefore any arbitrary element x belongs to h, this implies x belongs to generator of a to the power m. So this implies h is a subset of generator of a to the power m. Okay, so therefore we have h equal to generator of a to the power m. Okay, and hence h is a cyclic. Okay, now next, suppose order of generator of a equal to n and h is a subgroup of G. Okay, we already see that h equal to generator of a to the power m, where m is the least positive integer such that a to the power m belongs to h, and we also h is a subgroup of G, so that is, and also any identity element of a group is unique, so also E belongs to H. Okay, and from here order of generator of A equal to, we know that order of A, this equal to n given, so this implies a to the power n equal to identity, and from this we have a to the power n belongs to h and h equal to generator of a to the power m. So this implies n equal to mk for some k. Okay, because every element of h form as a to the power m some k. Okay, this form. So a to the power n belongs to h, so this implies n must be equal to some mk. Okay, so we have this implies m equal to n by k. So we have h equal to generator of a to the power m, that is equal to a to the power n by k. So this equal to generator of a to the power n by k. Okay, so h equal to generator of a to the power n by k. Okay, now next we know that any element a belongs to G with order equal to n. Okay, and any positive integer k, then order of a to the power k equal to n by GCD of nk. Okay, this is a famous result. So now using this result, now order of a to the power n by k, generator of a to the power n by k, this equal to order of a to the power n by k. So this equal to n by GCD of n and n by k. Okay, so this equal to n by k, because GCD of n comma n by k, this equal to n by k, so this equal to k. So therefore we have order of generator of a to the power n by k, this equal to k, that is order of h equal to k, and hence the proof.